Okay, good morning. So, welcome to today's seminar. And today's speaker is Dr. Cosme Gonzalez Ayani, who recently started working as a postdoc in the group led by Dr. Marko Kralj, under supervision of Dr. Ida Delac. He obtained his PhD at the Universitat Autónoma de Madrid, where he acquired his expertise in scanning tunneling microscopy and low energy electron diffraction techniques. And his main research focus is on 2D materials, including both their synthesis and the characterization. Also, the research focus is on superconductivity and superconducting materials, as well as surface chemistry and photochemistry. Today, he's going to talk about his research done at Universitat Autónoma de Madrid. So the floor is yours.
So thank you for the kind introductions and thank you for the authors for coming today. I'm going to talk about this 2D Kondo lattices in 2D systems. So mainly in this transition metal dichalcogenide that is tantalum disulfide. So just to introduce me again a bit more, I just finished the PhD 1 year ago at the Madrid in the Universidad Autónoma in the group led by Amadeo Vázquez de Parga. It's called the Nanoscale Imaging of 2D Materials group. So this group has facilities in 2 places, in the Autónoma campus and in the Institute of Nanoscience of Madrid. Many work there with STMs, and in this case they have 3 different STMs. So one that works at variable temperature, so between 30 Kelvin and 300 Kelvin, depending if you use a flux cryostat that microscope has. And then 2 low temperature STMs. This one here is an Omicron that can go down to 4.8 Kelvin for 23 hours. And another one is this also low temperature Joule-Thomson STM that can go lower in temperature, so 1.2 Kelvin for a longer period of time. It has a whole time of 100 hours. And it also has available a magnetic field produced by a superconducting coil, and this magnetic field is perpendicular to the plane of the sample. No? And all of the STMs have these other techniques like lead, QMS, and working into high vacuum. These are some of the research topics of the group. So epitaxial growth, chemistry and graphing, some integration of these 2D materials in devices, but this is done more in collaboration with other groups at the Indiana Nanoscience, and also this research on 2D materials at low temperatures. I collaborated more, I have more experience in epitaxial growth, chemistry and graphing, and these 2D materials at low temperature. And today I'm going to talk about the results of my thesis about these again, Kondo lattices in transition metal dichalcogenides heterostructures. So what's a Kondo lattice and where can we find these Kondo lattices? So Kondo lattice is a quantum coherent electronic state that has been mainly measured in heavy fermion materials. So these materials exhibit a strong electron correlation. Okay, they are mainly 3D systems, and here are an example of most of them. That, as you can see, they all contain either rare earth elements or actinides that have these localized electrons in their 4f or 5f orbitals. So you can picture these systems as a lattice of magnetic impurities because of these rare earth or actinide elements embedded in a metallic crystal. So like two examples are here with uranium and with yttrium. And basically the strong electron correlation physics that appears in this system is due to the interaction between the magnetic moments of these localized electrons and the highly mobile or the itinerant electrons of the metal. Okay? So it's this interaction that defines what's going to be the ground state of the system, and this ground state is determined by the competition between 2 effects. One is the Ruderman-Kittel-Kasuya-Yoshida interaction that we call from now onwards as RKKY, and the other one is the Kondo effect or the Kondo gap. Okay, so just to introduce these 2 effects, these 2 interactions, because it's going to be easier to follow in the following slides. So both the Kondo coupling and the RKKY interaction are many body effects. They involve a magnetic moment interacting with the conduction electrons of a metal. Okay. In the case of the Kondo effect, in the Kondo coupling, this effect emerges when the conduction electrons are screening this magnetic moment. Okay. This screening is produced by a scattering and a spin flip process in which the spin of the magnetic moment is flipping between the two possible directions. From this effect, although it's not done at an atomic level, it has macroscopic consequences on the resistivity of a metal. So normally, if you have a metal and you decrease its temperature, its resistivity is going to fall until it reaches a more or less constant value. However, if this metal contains magnetic impurities, for example, from other elements like cobalt, what you're going to find is that below a characteristic temperature called the Kondo temperature, this resistivity is going to start to increase again. And this is due to this screening of the magnetic moment with the conduction electrons and this scattering. You know? Thanks to STM, this Kondo effect has been measured at an atomic level. That is just so in the simplest system possible, it is just a magnetic atom of, for example, cobalt on top of a metallic substrate. When you measure this system with an STM, and you can do, for example, scanning tunneling spectroscopy, the fingerprint of this effect is this zero bias resonance that appears here at 0 voltage. So this is the fingerprint of the Kondo effect with STM. Normally, if you have more than one impurity and you start to bring them close together, what you're going to have is that this the same exchange coupling that was produced in the Kondo effect is now going to also try and couple the magnetic moment of these impurities, of these impurities. No, so they are coupled together but mediated by the conduction electrons of the metal, meaning that they can order either ferromagnetically or antiferromagnetically, and this is going to depend well on the distance between the magnetic impurities or the magnetic moments, and also the temperature. It's going to affect the coherent length of the electrons and how they are displayed or how they are organized or what is their relative position. No? They have also been, or this interaction has also been measured with STM, but it's measured indirectly, and it's what it appears in spectroscopy is this gap or set of gaps that are related to a spin flip process when an electron from the peak tunnels into the magnetic field. So there's a lot of information here, but the take-home message is that in a heavy fermion system, you have these two interactions competing with each other. The Kondo coupling is trying to screen the magnetic moments, and the RKKY interaction that's trying to order them either ferromagnetically or antiferromagnetically. And therefore, there are two possible ground states regarding this interaction. So this is shown here, or depicted here in these Doniak phase diagrams. If we don't take into consideration any external force or something similar, there are only two possible ground states. One is magnetically ordered, that is when the RKKY interaction is stronger than the Kondo coupling, and then therefore you have a magnetically ordered ground state with a small Fermi surface. And the other one, this is one interesting for us, and we are going to show today, is this heavy Fermi liquid phase that is also referred to as a Kondo lattice. In this case, what happens is that this phase is paramagnetic, and it's described as the formation of heavy fermion quasiparticles that are composed of this magnetic moment and the conduction electrons of the metal that are going to screen the magnetic moment. And there's an increase in the Fermi surface of this material whenever you end this ground state. However, we're not going to study this Kondo lattice in a heavy fermion material. We're going to study it in a 2D material, and this 1T2H tantalum disulfide van der Waals heterostructure. So tantalum disulfide, as I suppose most of you know, is a transition metal dichalcogenide. This is the typical chemical formula of a transition metal dichalcogenide, where M is a transition metal and X is a chalcogen. And one of the main interesting properties of this material is that they exhibit different electronic properties. First of all, depending on the possible combination of the three chalcogens with these transition metals, but also depending on the two possible polymorphic phases of the transition metal. These polymorphic phases depend on how the three chalcogen atoms are coordinated with the transition metal. If the coordination is diagonal, then you have this H phase, and if the coordination is anti-prismatic or trahedral, then you have this E phase. One interesting example of a chalcogen, a transition metal dichalcogenide of the same chemical species that has very different electronic properties between the two possible polymorphic phases is tantalum disulfide. So the two phases of tantalum disulfide, the 2H and the 1T, shown here, as I say, they have very different electronic properties at low temperatures. And the 2H phase has mainly a metallic character. When you decrease the temperature below 78 Kelvin, it has a charge density wave transition where a 3x3 charge density wave appears. And in STM, it shows this charge density wave pseudo gap of more or less 15 electron volts. This is the main fingerprint of this 2H tantalum disulfide in scanning tunneling spectroscopy. Also, when you go below 0.8 Kelvin, it has a superconducting transition, but we're not going to be able to go there, so it's not important for us. The 1T phase has a much richer charge density wave phase diagram. It has many charge density wave phases. The one we're going to see today is below 183 Kelvin, and where this root square 13 by root square 13 rotated 13.9 degrees appear, charge density wave appears. The unit cell of this charge density wave is comprised by what is known as a Star of David cluster that is shown here. So this Star of David is composed of 13 tantalum atoms, and when the temperature goes below 183 Kelvin, the 12 outer atoms contract towards the central or 13th tantalum atom. This contraction produces this charge density wave and makes that an unpaired electron is localized in this tantalum atom. This localization produces a metal insulator transition, so the 1T is not metallic below 183 Kelvin, it's a Mott insulator, and therefore when you do a spectroscopy, what you observe is a Mott-Hubbard gap, with a lower Hubbard band and the upper Hubbard band, okay, more or less of 300 millimeters. This is the sample we studied. It's a commercial 2H tantalum disulfide crystal. Okay, we cleave it in UHB, and it's adhered to the sample holder with a silver epoxy. We also adhere close to it a gold ball that we use to prepare in situ our STM tip. So with the shields closed, because we have another optic port, we can prepare our sample without opening the thermal shields and therefore contaminating it. No? So we can withdraw the tip, move it, just so it's below the gold ball, indent it there a couple of times, and go back to the sample. And if you do it carefully, counting well the steps in voltage, you can more or less get back to the same area where you were studying before. Yeah, so this, and therefore we're also going to work at two temperature regimes, 52 Kelvin and 1.2. When the surface of the sample after cleave is relatively clean, this is an image of more or less 2 micrometers. And much to our surprise, at the start, what we saw is that both polymorphic phases of tantalum disulfide coexist in this sample. So you have in the surface of the sample both the H and the T phase. And we explain this because the formation energy, or the difference in the formation energy between the two polymorphic phases is very small. And therefore, when you cleave or when the sample is grown, you can have these two polymorphic phases coexisting. Therefore, we understand that we have these 4 different possible terminations of these possible systems in our sample, depending on which or how is the surface terminated. So the simplest case would be 2H terminated. That is in theory the crystal we want. And then you have this 1T terminated, meaning that the first 2 layers would be 1T. And then these are the most interesting cases, in my opinion. First, the one is 1T heterostructure, so you have a H layer on top of a T layer, and then the 2H crystal. And the one I'm going to talk today is this 1T2H heterostructure, so you have a 1T layer on top of the 2H crystal. We are able to identify this heterostructure by means of single layer step edges, like the one shown here. So the area to the right is the 2H crystal, and the area to the left here is this 1T area. Then more or less the height of the single layer steppage is the one expected, so 0.6 nanometers. The corrugation you're seeing here is not due to the atomic corrugation, but due to the corrugation of the charge density wave. This is the corrugation of the 1T charge density wave that is much more corrugated than the 3x3 of the 2H layer. We have studied the atomic periodicity and the periodicity of the charge density wave by means of fast Fourier transforms. So we are able to obtain steering images with atomic resolution, and then we can fast Fourier transform them to study the periodicities. Here in purple, the atomic periodicity of the 2H, in blue, the spots of the 3x3 charge density wave, and here the same thing for the 1T, where the spots of the 1T charge density wave make an angle of more or less 14 degrees with the atomic lattice spots. So the values of both the atomic and the charge density wave periodicities are expected. So there's no major changes on the lattice parameter of the systems when the heterostructure is formed. This is not the case with the local density of states. While in the 2H case, we do see what is expected, so there's nothing new. At both 52 Kelvin and 1.2 Kelvin, you see this charge density wave pseudogap. It is the expected and the one reported in literature. However, when you go to the 1T phase, so in this area here, what you see first of all is that your lower and upper Hubbard band appear at different energy positions. So they are renormalized because now you have below a metal. And when you go down to 1.2 Kelvin, this strong zero bias resonance appears at 0 voltage that we believe is a Kondo resonance. And it's what I'm going to try and demonstrate in the following slides. So this zero bias peak, this Kondo resonance is modulated spatially. Its intensity is modulated spatially with the periodicity of the 1T charge density wave. So it's more intense on top of in the center of the Star of David, where this unpaired electron is localized, and its intensity is reduced as you move away from the center of the charge density wave. So we believe that therefore this peak is related to this localized unpaired electron. And then we've also studied, as it's typical in this system, try to measure the Kondo temperature of our Kondo impurity. No? To do this, we have to measure how the full width at half maximum behaves as the temperature is increased. So we perform temperature variable measurements. The Kondo resonance are fitted with a Fano function. This is this one here, where gamma is this full width at half maximum. And then if you plot the values of the full width at half maximum as a function of temperature, with this equation here, you can measure calculate the Kondo temperature. In this case, it's 27 Kelvin, but it's in good agreement with our previous results that at 52 Kelvin, we didn't see any Kondo resonance. Okay, so up to now, I'm going to do a brief summary. What we believe is happening here is that you have an unpaired electron at the center of each Star of David cluster. So this is the one is a mod insulator, and below you have a metal. The electrons of this metal are screening this unpaired electron, and therefore when you do STS with the STM, a strong zero bias resonance appears. So what you have basically in the surface of the 1T is a periodic array of independent Kondo impurities, okay? And this is similar to what you have in a heavy fermion 3D metal, you know? This lattice of magnetic impurities embedded in a metal. However, there's some difference. It's a 2D heterostructure, and because the periodicity of this array of Kondo impurities is the one of the 1T charge density wave, it's a triangular lattice. So therefore you have magnetic frustration. Antiferromagnetic ordering is forbidden. No? You cannot have antiferromagnetic ordering in a triangular lattice. So therefore we believe we have all the key ingredients for the formation of a Kondo lattice. So now the question is, okay, what do you measure when a Kondo lattice is formed? No? And this is, well, you can understand this with the Kondo lattice model. I've got this information from this article here that is from 1982, so the idea is quite old. And I try to summarize it. If you want to learn like all the stuff, it's right here. So this Kondo Lattice model contains two effective temperatures. The first one is the Kondo temperature that I already introduced, and the second one is the Kondo Lattice temperature that I'm going to introduce. So when your system is below the Kondo temperature but above the Kondo Lattice temperature, both so the 1T layer and the 2H are decoupled. Okay, there's some interaction because the conduction electrons of the 2H are screening the moments of the localized electron, and therefore when you do this spectroscopy, you see the zero bias resonance. Okay, but you have this periodic array of independent Kondo impurities. When you are close or you are at the Kondo Lattice temperature, what happens is that these periodic Kondo impurities are no longer independent. Okay, they are now electronically coherent. They are electronically coherent and with the periodicity of your crystal. Okay, so the Kondo cloud is like this magnetic moment with your conduction electrons screening it, start to overlap each other, and they become electronically coherent. They become electronically coherent with the periodicity of the crystal, and therefore, with Bloch theorem, this thing means that you should have a flat impurity band appear close to the Fermi energy. However, this flat impurity band is now crossing with some of the conduction bands, meaning that in theory they have to, this should be forbidden, and therefore this conduction band is not going to hybridize with this impurity band. The hybridization of this band means that your localized moments are no longer localized, they become delocalized, and the conduction electrons that were screening it are acquiring a lot of mass, and therefore here you have your heavy fermion quasi-particles. Okay, these heavy fermion quasi-particles are then accommodated in your Fermi surface, and this is why you supposedly have an increase on the Fermi surface of your system. More important for us is that because the flat impurity band has hybridized with the conduction bands, you have now a gap here, and therefore what you expect to find in your local density of states is that a gap-like structure appears superposed with your Kondo resonance. So we want to try and measure this, and to do this, we are going to try and optimize our resolution. And we can do this in two ways. So first of all, measure at the lowest possible temperature, in this case it's 1.2 Kelvin, and then increase or approach our instrumental limit. We do this, in this case, by decreasing as much as possible the modulation of the locking of the SDLs. That in this case is 200 microvolts. And when we do spectroscopy, so this is the average of maybe 100 or something spectra, we observe this gap that has appeared on top of the Kondo, so superposed with the Kondo resonance, and we believe marks that we are in this Kondo Lattice regime. So we'd like to measure this Kondo Lattice temperature. So again, what we have to do is do temperature variable experiments and study how this gap evolves with temperature, but we're faced with the following problem. Because the gap appears superposed with the Kondo resonance, and therefore to study its form is very difficult. And our approach is the following. We do this temperature series increasing the modulation, so that's why the gap here appears with not as good resolution as in the previous slide. We're going to fit our spectra with the final line shape, but we're going to avoid fitting the area where the gap appears. So this area from -3 millivolts to 3 millivolts. So we're going to fit this area here of the spectra and this area here. And we believe that this final line shape should represent the Kondo resonance without the gap. So the pristine Kondo. No? If we then fit the experimental values with a polynomial function, we can calculate this blue area that we believe is related to how the density of state is depleted due to the appearance of this Kondo Lattice gap. To try and validate this fitting approach, we basically do the same thing we did previously with the Kondo resonance. So we're going to draw a plot showing the full width at half maximum as a function of temperature. And what we obtained here in this case is that, again, the same Kondo temperature, that is 27 Kelvin. So in a way, we are validating our fitting approach. If now we plot this how this blue area evolves with temperature, we get this plot diagram here. So this is how the blue area is decreasing with temperature, and more or less it becomes negligible close to 11 Kelvin. So this is the Kondo lattice temperature we propose. And this behavior cannot be only due to an increase of the thermal energy. To make sure of this, we've done a very simple model where you superpose a 3 millivolt gap with a Kondo resonance, and then you do the convolution with the Fermi-Dirac function just to broaden the gap with temperature. And this is the expected evolution of a gap broadening with temperature, and as you see, the behavior is quite good. Okay, so now I'll finish with the take-home messages. So we've studied a 1T2H tantalum disulfide heterostructure by means of STM. Although it's a van der Waals heterostructure, the interlayer interaction is strong enough to produce this Kondo effect between the localized moments at the center of the Star of David cluster and the itinerant electrons of the 2H area, the 2H phase. We find a Kondo temperature of 27 Kelvin, and then we're able to measure the transition to a Kondo lattice that occurs more or less at 11 Kelvin. So therefore, we are realizing the 2D Kondo lattice in a 2D system without any F electrons, as it happens in other heavy fermion materials. With this, I'd like to end, thanking the audience for your time, and thank you.
Okay, any questions?
So the metallic layer below the 2H. So do you have any indication of possible charge transfer into the 1T layer, or you just claim that the electrons localized in the 2H layers are making the screening?
So the electrons localized are in the 1T. So in this more insulator, the 1T, the
topmost one.
Yeah.
Yeah.
So,
but the screening comes from the 2H below.
Yeah. Because it's the metallic. So the 2H is metallic. It has the conduction electrons, and these are the ones screening the 1T.
But I'm wondering, is there a charge transfer effect, or it's just enough? Let's say proximity is enough that the screening is effective.
So we didn't do any DFT to see the charge transfer that we haven't done any. Most of the calculation was to, well, the theoretician group did was to model these bands of the 2H crystal, and then also like this impurity band, and see how they will hybridize to make this gap. And that more or less works. But I don't know if there's charge transfer.
Did you make some comparison with DFT results on this study? I'm not sure what are the autos, but I remember that there are some DFT calculations of this Charlotte wave where you have where they get this gap opening, and then they get localized state at the Fermi level only from the distorted DFT result. So did you find so many results in the literature?
I know there are some DFT what they claim like this in other materials, or in this PoHB they claim there's this sharp states inside the gap. Yeah. But I believe this is not the case. So here this sharp resonance here is a Kondo resonance produced by the Kondo screening of the 2H layer. And because of these reasons here, also it's modulated with your 1T layer, and then it shows the expected behavior for a Kondo resonance.
More questions?
Yeah.
So the underlying 2H layer is metallic.
Yeah.
Okay. And if you have bulk 2H, it will be metallic as well.
Yeah. So you have a metallic sample below your 1T layer.
Right.
So it's like taking into consideration that these are mostly referred to as quasi-2D crystals because ideally the interaction between the layers is van der Waals. So
you wouldn't have stars in 2H.
No. So in 2H, actually, when this 3x3 sensitivity wave appears, the formation of the lattice is very small. It's much stronger here.
Right.
And actually, you have this transition to a sensitive wave, but also a metal-insulator transition. That this in 1T crystals is discussed. It's really a metal insulator, but in single layers, there's more or less agreement. Sorry, between in the literature that a 1T single layer is a metal insulator.
Would this work with any metallic substrate in the interaction with regionals, like van der Waals?
Yeah.
So it's not specific to like some structure underneath. It doesn't have to like be, certain fermion shell or something like that.
I suppose it has to be the interaction weak enough so that there's not a lot of charge transfer. But you need a number of electrons a system that has a number of conducting electrons enough to screen your magnetic impurities. In this case, are these star of David clusters. And yep, so I think yeah.
I have another one. So you are aware that if you have stars in a self-bending, so to say, 1P system,
yeah,
you have a 1 electron per star basically, which you now model as a spin state, but you don't have electrons. Okay, in that case, without a substrate,
yeah,
you don't have electrons. You don't have a conduction band.
no,
right? And then if you consider this is terminology, if you consider van der Waals state, it's an interaction without actually exchanging the electrons. So there is no conducting. So essentially, this is just the terminology. It's not a objection to the results or to your picture. You have to have some sort of hybridization. And this is usual Kondo model. You have hopping between, or Anderson model, if you like. You have to have hopping between the electrons, metallic states, and spin states. And in that case, it can only be the van der Waals.
So yeah, I understand what you mean, and I'm totally in agreement with you. The thing of these systems is that they are normally said as van der Waals heterostructure, and it's believed that they interact with van der Waals, but there are more and more articles now that when you start to increase the temperature,
there's always a big hybridization.
There's always something happening, and the ground states are very rich. So in the case of, we can discuss it later if you are interested. In this case, we also see an effect of hybridization or
interlayer coupling.
Right. So basically, we're able to observe the challenge wave of the 1T layer through the 1H. And we can modulate that, how we observe that challenge wave with the voltage of the.
And this is what makes your metallic valve for spin, right?
Yeah, I think so.
You maybe first.
Just question about this terminal surfaces, because you have a very different combination of the terminal surfaces, and how do you specifically get what you is it that you just previous sample any sample try to find the ratio?
So at the start it was a mess because I didn't understand anything. I was just measuring here with an STM and finding different charged waves. So at some point I started to understand that you usually find like these locations, or you can see that there's different correlation here. But well, the only thing we do is clean the sample. We don't anneal it or nothing else.
Do you
Just
try to grow in situ?
we try to grow in situ, but normally it's one layer on top of graphene iridium or HOPG. Actually, you are able to change the 2H phase to a 1T with your T. So actually, this is what I here. This area here is the H, and this is the T. And by doing a voltage pulse, you can change from one to the other. Here. You destroy the area when you do the pulse, but then you can get this like this polymorphic transition from H to T.
Yeah, in the same direction, I just wanted to ask, did you observe any sharp lateral 1H, 1T junction?
No. So yeah, it's like what they see in literature is that you just move the top layer of sulfurs, they are rotated. When you get this pulse, you give enough energy to rotate itself, and then you have like this location here where suppose you have a mirror tube value or something, and you go from one to the other.
Now, you mentioned that you were able to grow it on graphene and iridium. Which phase do you get? Like 1T, 1H, or
you get if you grow it at room temperature, you get 1H. There are some articles there where if they with a higher temperature, you can promote 1T. I haven't tried, but you can find that. And then in HUPG, I found that there were some areas of the islands that had a little like a dislocation, and I believe that maybe they were at some point when they are growing, they were 1T and they changed to 2H or something like that. But yeah, you can grow both phases. The most stable one is the H.
Are there maybe questions from the online audience? Never. No. I think there's a message in the chat, but it's for a long time. There is one message in the chat, yeah. Or? Okay. Yeah, in that case, let's thank our speaker again.